Really great to have everybody here for the Building Performance Interactive. And we're excited to get going into the show in just a moment. Before we do, I wanted to thank Hugh Bariski and Yulia Potor of Partel for helping us create this series. We're now in the second season, and so it's been very gratifying to collaborate with Hugh and Yulia. And I am going to be playing the role of Q&A concierge today during the presentation. So as questions occur to you during the show, please type them into chat and we'll be tracking those for you. And then when it comes time for the Q&A discussion at the end of the program, we'll be inviting folks to come on screen and ask their questions directly of the presenter. So without further ado, I'd like to introduce our co-hosts, Ben Adam Smith of House Planning Help, Hugh Bariski of Partel, and Mike Jacob of Kiss House. So gentlemen, please take it away.
Thanks, Zach. Welcome everyone. So delighted to have, I suppose, a real expert on today and to get an insight into what's I guess a pretty misunderstood and changing area. So really important and has lots of impacts in, I suppose, how we're going to build better. So yeah, looking forward to seeing what Declan has to say. Over to you, Ben.
Yeah, fire safety. I remember I did some filming a couple of years ago at Grenfell at the base, just with the communities that surround that area. And yeah, you get a sense. One of the things that surprised me was that they were really keen for sustainable construction and better construction. So I'm hoping that that's also going to come out as part of this fire testing and rigor that goes through it. So over to Mike now.
Thanks, Ben, and Zach, and Kim, and everyone, and Hugh, of course. It's great to be back. Looking forward to learning a lot from Declan today. It gives me pleasure to introduce Declan Wallace, who is the CEO of Evolution Innovation, which is an international multidisciplinary engineering consultancy providing structural engineering, building physics, product development and project management of third-party certification of construction products and systems. Evolution specializes in high-level MMC consultancy in the design and development of 2D panelized Category 1 and 3D volumetric Category 2 and traditional building product-led site labor reduction and productivity improvements. So with over 20 years in MMC, Declan is recognized internationally as a leading expert and has been instrumental in developing a range of MMC products currently in the Irish and UK markets, and is also acknowledged as a building regulations expert. And in 2022, Declan was a founding member of MMC Ireland and is the chairperson on the board of MMC Ireland. It gives me great pleasure to hand over to you, Declan. Take it away.
So today's talk is going to be on structural fire safety testing in offsite systems, which manufacture energy efficient systems. So I'll start off with just a quick introduction who Evolution are and what we do, and then we'll get into the testing. So Evolution are, as Mike said, we're an internationally recognized consultancy. We specialize in the MNC sector. We're unusual in the offer kind of a one-stop shop in that we've all the expertise in one house. We've an unrivaled team of experts, and to date we've been involved in over 2.75 billion worth of MMC projects, varying from Category 1 to Category 2. And so we're experts on regulations. So just a quick brief overview. We're in existence 12 years. We've grown to 45 in the team, 4 office locations, and our plan is to go to a 6 million turnover in the next 3 years. So we're world experts in panelized and modular construction, as you'll see there. So you're seeing some examples of kind of what we do. And basically, we're comprised of 4 departments within Evolution. So our first department is structural engineering. And we specialize in light gauge steel and 3D volumetric design. The second area is really in the R&D sector, and this is where today's talk will focus on. And we specialize in getting third-party certifications for MMC products. And we help companies develop the products, and we manage structural fire testing. So we would do about 75 structural fire tests a year, varying from all sorts of tests, that'll be a lot every year for different manufacturers. Our new area of expertise is we're going into thermomechanical modeling for high-risk buildings, so particularly high buildings where we do a lot of heat transfer modeling, thermomechanical modeling. It's a new area coming from the Building Safety Bill in the UK. And also we have the sustainability department, which focuses heavily on embodied carbon value engineering. So it's a big part. Obviously, embodied carbon is huge, and we have a big department in that. So as you can see, it's all interlinked. We have structure, we have sustainability, and we have fire, basically. So just we offer loads of certifications, and all these certifications are, where appropriately, are third party independently certified. So the final slide on us. So just to show you our track record, we've done over 2,000 educational buildings. We've done 2,000 healthcare, 8,000 hotel beds, over 10,000 in the resi sector, and over 12,000 student accommodation sector, all in the MMC sector. And we're central to developing and certifying over 20 different building systems in the UK and Ireland. So today, as mentioned, so most of you are probably familiar with the categories of MMC, but in the UK and Ireland, I'm conscious we have a lot of people from the States here on the call today. So, we have these 7 categories. I'm not going to bore you, but today we're going to focus on category 1 and 2. So category 1 is 3D volumetric, and category 2 is what we call a structural panelized system. So we have the other 7 categories. Now we work in the other areas, but today's topic on fire is going to focus on the first 2. So just so we're clear, on the left-hand side there, you see a typical category 1 system, which is a 3D volumetric system. And on the right-hand side of the screen, you see a typical structural LGS system. And all the systems on today are structural. So you can see the difference in the technology. So one is a 3D volumetric, and the second is a 2D panel system. So why are we doing all this, right? It's got to do with building safety and compliance, and obviously one of the other speakers mentions the Grenfell Tower, and out of that came the Hackett report. And what you're seeing here is the Hackett report identified a lot of shortcomings in construction in general. So as you can see, we have the drivers of compliance, we have this building regulations, building control legislation, codes of practice, etc. I suppose the key thing that came out of the Hackett report was offsite systems and the importance of system-specific testing. So what's very important is all these new MMC systems, they work very well once they've been properly tested. So the key question is, has the offsite product got the system-specific testing? And that's what we're going to discuss today and how we'll go about that. So today we're going to focus, as I said, on fire resistant category 1 and category 2 structures. So before we get into that, I'd just like to clear up something what we find from a lot of people in the industry about non-combustible products. So we have a standard called EN 13501 in Europe, and that recognizes combustibility of products. It's very important that everyone on this call understands that non-combustibility does not mean any good fire resistance. So you can see there, it's very important, the classification of fire spread, but that's got to do with flame spread, ignitability, smoke production, heat release, and capability producing. So it contributes to the fire. But what's very important is the misleading thing we get here on some of these products is that, say a non-combustible product doesn't necessarily mean the product is any good at fire protection. It just doesn't add to the fire. And that's key. And a lot of people, we come across people using products and materials that may be non-combustible, but they would have no fire resistance, and they're being used in fire resistance situations. So it's very important people understand the difference of non-combustibility and fire resistance. They're not the same at all. So example of products would have, and obviously A1, A2 is ideal. So brickwork, you can see steel, concrete, they're all A1, gypsum-based boards are A2, and then we go down the line to say wood-based products would be D. So like some OSB board, PIR insulation, different types of, etc. So but the key thing here is it doesn't guarantee fire resistance. It's very important. It is very important, and obviously if you can use an A1 or A2 product, fantastic. That's better, but it doesn't provide fire resistance. Okay, so today we're going to talk about testing regards walls, floors, indicative testing, column testing, penetrations, and BS 8414 and full-scale testing. So just a quick one, and this is the same table, basically it's in the UK regulations, and I'm going to focus obviously on the Irish and UK regulations in particular in this talk. So the key thing here we're showing here on this slide is what we call REI, which is the REI of the walls and floors, and all I'm talking today is structural fire testing. So we're really focusing on structural fire testing. Okay. So before we get started, and this is common to the US and UK, we have a standard for plasterboard, and what came out again of the hacker report is that when you look into this in the standards, the plaster manufacturers went back to the statement: resistance to fire is a characteristic dependent on the assembled system and not the product in isolation. So just because you have a product, a board, for example, and most of these systems are protected with some sort of board. The key thing again is even the standards tell you that yes, the board has a resistance, but it must be tested with the system, and it's so important you have to test the system. Okay, so without getting too sciencey on you, so what you're seeing here are the fire curves we test to. So in Europe, we've switched to the blue curve, which is called the standard ISO curve, which is the curve you can see here, the blue curve. So we used to have a BS, the old BS curve, but this is a more severe curve. So all the testing we do in Europe is to the blue curve, and that automatically covers the UK as well. So it's a standard curve. So that's the key curve there. So all our testing. And this is a very severe curve, and much more severe than what we call a parametric fire. So a parametric fire curve would be a real natural fire situation. So it is fully accepted that these fire curves are very severe and meant to be very conservative from the point of view of their worst case scenarios. Okay, so starting off with a simple, these are load of wall tests. So we typically do load of wall tests. What's key about these are done to something called EN1365, part 1. So what's key here is the adequate detailing of surfaces. So have we tested surfaces in the walls? The importance of load is critical, and temperature steel for the duration of the test. And all testing is generally with type F boards. And this is very important with fire resistant boards. So today, when we talk about modular and panelized, we're really going now. We work in timber as well, but we're really going to focus on steel today because steel tends to go a lot higher, and we go quite high with some of these buildings, as you'll see. So today we're focusing on steel primarily for the example. So just showing you here visually to what a test looks like. So it's basically a 3 meter by 3 meter test. What you're seeing here on the outside is the back of the test rig with all these loads of thermocouples. What you're seeing then on the second picture would be the exposed in the furnace side when it goes into the furnace, and you can see there, for example, we've sockets included in these to test the sockets in the wall. And what you're seeing then on the inside is a view from inside the furnace, through at a period of an hour or so through the test. So you can see the severity of the fire and how the wall was performing. Again, we go on the test again, and you see now this happens to be quite a long test. It's kind of a 2-hour test, this particular test. So you can see here the first board has fallen off, and the second board it has kind of lasted. And you see here in this particular test, it's a particularly long test. This one, this is after the test, and you can see that this was after it's been pulled out of the furnace. That's what the inside of the panel looks like. Now this test would have passed, as you can see, because on this one you just about see it lasts just over 2 hours, for example. So this is the unexposed side. So, and this was the inner side. So it's just an example of how visually how a loaded test works, and they're very severe. So just a very quick one on testing. So what's very important when you do testing is you need to understand that you need to know what you're doing. And it's not where Evolution assists here is that we design these tests to comply with the test standards, but also that we're getting additional data for future assessments. And that's very, very important, because all the labs we use are UCAS approved, and they cannot consult, they cannot advise you. So when you go to a test, they will let you test it incorrectly because they'll just say the test is not compliant. They're not allowed consulting. There's very strict rules around their certification, so they cannot consult. So that's where we come in and we advise how you do these. And what you're seeing here is we're putting thermocouples on the steel studs. So even though this is not in the test standard, this is more important than the test standard was, because we need to know the temperature to steel. So it's very important, even though that's not in the standard, you have to do this. It's very important. So, and why is this? Because steel will reduce as it gets hotter. So the hotter the steel gets, it has a thing we call a strength reduction factor. And again, here, when we talk about sections, so there's a myth about steel and steel, so when we talk about steel, we got class 4 sections and a class 1 section. A class 1 section would typically be a hot rolled steel section. But in practice, there's very few hot rolled steel sections used because it's quite an expensive steel. And with class 1 sections, they lose their strength at 550 degrees, but other sections lose their strength much earlier. So it's very important that we're tracking the temperature of the steel. And that's more important almost than the test passing itself, getting the REI. Okay, so why is load so important? Is because the studs should be not designed to more than 80% of their axial capacity. We look to term of Boeing, and we have a load ratio, and not to bore you too much, but ultimately then the steel is tested to approximately 50% of the actual load, and the fire limit state is 50%. So what you're seeing here again on the screen is an example of one that would be tested, and this is a 30-minute test, and you see it got 41 minutes. And we always test to this. We generally always test to destruction because that's very useful. We like to get an extra 10% in our test, so this is really a 30-minute test. And we like the longer we're getting information, we're getting more information on how the steel is reacting over a period of time. So this would typically be a single boarded fire test. Okay. So driving factors. So there's 3 key driving factors when it comes to looking at one of these tests. So temperature is key. So as the temperature increases with time, the strength of steel reduces. So dependent on the board effectiveness and insulation. So that's very, very important. So how hard the stud is working in a fire situation is also, it's called the fire limit state. That's very important as well. And then, of course, we have the cold capacity of the stud. So what is the normal capacity of the section in as it's designed in one? Now, I don't want to confuse too much, but this is very important and it can be very complex. So this is really structural fire engineering, and you need to understand this. And that's why when we do these tests, we really are obsessed with the temperature data of the studs, and then we know what the studs can be designed to, and that should ultimately be checked by the structural fire engineers, and hence that's why we have a structural fire department, and that's why our guys would check this in their calculations, which is very important. So a very good document which we're involved in, which we contributed to a couple of years ago, and it's well worth being aware of, is a publication called SCIP 424. And it's even though it applies to modules as well, but it's an excellent document which provides loads of guidance on all sorts of anything to do with fire and panels and modules. So it's an excellent document, and I couldn't but recommend that you get your hands on a copy of that if you're doing any panelized construction whatsoever. One other key point to highlight in this document is just to highlight that we get asked this question a lot. So as I said, we're generally testing in a lot of cases class 4 sections. So when we have a test with a class 4 section, that would basically be a light gauge steel section, maybe 100 by 1.2 millimeters or something. We would have hot rolled posts in between the studs. So does that need a different test? Well, the answer is no, because it's a heavier section. So the heavier the steel is, the slower it heats up. So if we test lighter steel and we have the temperature of that and it passes, then we can obviously use heavier steel, and by default that would heat up slower with the same protection. So it's just an important note. We get asked that quite a lot. Okay, so another test on the low bearing testing, and a new phenomenon that's happened in the last couple of years is, especially with Grenfell, is out-to-end testing. Now, this is not to be confused with BS 8414 testing, which we'll show you shortly. So this has got to do with this got to do with protecting the wall from out to end. So this particularly comes to play where we have, say, a building that would be maybe a 90-minute building, and the external walls of the building are structural walls, and these walls then would have lightweight cladding. So generally, we look at lightweight cladding. In most situations, the lightweight cladding might be a terracotta or a rain screen or an Ecotone, a cement board product or something. So basically, they would be open joint systems. So we would assume that there is no fire resistance in the outer cladding, and therefore we assume the fire is attacking the wall from inside the cladding. So we generally don't test these with claddings. So this is a very popular test, and we do this now with all our systems now to prove that if there was a fire outside the building, I know it might seem severe, but we have to look at that, especially when we come to relevant boundaries and neighbouring buildings. This is also very important. But you could technically have a fuel load outside the building, maybe a bin store or something outside the building, and we have to manage that. So it's really for external lightweight claddings. Now, you can use this curve 13632, which is slightly less curve because basically, you know, the fire is outside and it wouldn't have the same fuel capacity as a compartment fire. But we do recommend where possible do the higher curve. In this case, the curve reaches 650 and the fire resistance. And this is important. We only require an R requirement here, not an installation integrity. This is protecting the structure. So again, just on this one, when we look at the blue curve earlier on, which we test all our elements to, you can, on certain situations, use the green curve here, but we would recommend where possible use the blue curve because it's a more severe curve and it keeps everyone happy. So that's kind of walls covered. Now we'll just touch on floors. So what we call EN1365 Part 2. So it's a different rig. It's a big wide rig. This one is quite a different test. So this is a different approach to this one. So the service strategy is critical. The importance of keeping boarding in place is very important here because unlike the walls, yes, they're screw fixed, or the case is, but we have gravity to come into play here. So often what happens here, if the fixing get too hot, the boards actually fall off. So the boards actually haven't lost their integrity. The fixings have got too hot and the weight and the gravity pulls the boards down and you can get premature failure. And that's why it's so important to test these floor systems to make sure that when we test these fires that the boards will remain in place. So the strategy of keeping the boarding in place absolutely critical. Can't mention that enough. And in failure is generally caused by boards falling down and results deflection. And then you'll get very quick integrity failure. So once that boarding fails, you will generally get failure within a minute or two. It happens very quickly. An interesting note on modular construction, where we use these sets of floors in modular, they generally perform better than a standard floor, and that's because the ceiling is generally unloaded below, and that tends to last quite a long time. So from our experience now, it depends on the system. We get better fire performance in modular floors. This is just, again, we always test the destruction, and there's an example of what would happen when we've tested destruction. Again, what we're trying to show here is the strategy for the services on the floor. It's very important, that we would have services running in service voids here that we don't have services here. And different codes in different countries require this, but in Ireland, for example, we don't we don't have services running within the floor. We are allowed to run a service vertically through a floor and a shaft system, but we're not allowed to run a service within the floor. So we generally counterbatten or use suspended ceilings underneath the two layers of fire protection and lining. Okay. Again, just showing you here, this would be a typical intermediate floor. So an intermediate floor is a floor that would be used in a domestic house. And something that people don't realize is that floor is a structural floor. And that floor has a requirement to be protected for 30 minutes. And it should be protected. And therefore, in Ireland now, for example, any penetration to that floor has to be fire protected. So what you're seeing here is an example of how you would put, even if there was a vent or a range on the floor, how you put a proper collar and the grounds you need for that collar to put that collar in properly. And they must be done by licensed installers. Okay. So just closing out on that. So there are fire tests. What we can do after that, and we're very limited, we can do a thing called a field of direct application. So what that means, once we've done our testing, so, if we use two 12.5 mil boards, we can increase the boarding, we can decrease the height, but the field of direct application is very limited. It's very important. So we can do small things, but it's very limited, okay? And it's very, very conservative. So it's kind of only stating the obvious, really. Okay, so a new lot of work we do now is heat transfer models. And what are these heat transfer models? So heat transfer models are where we have the data from these fire tests. We get the properties of all the materials. Now, this is very specialist stuff. We've started doing a lot of this with loads and loads of data, and we're able to model these scenarios really, really accurately. And that really helps when we plan future testing, knowing the tests are going to pass, or it can also help when we have a slight different situation in a building, and it would avoid us having to do another test when we have real data on similar materials and properties. So what you're seeing here is a wall that we're currently doing. You're seeing the model running, and this is just exposing the stud from kind of two sides just give you an example of how the stuff heats up and monitoring. So a very kind of specialist work, and we do a lot of that kind of stuff. So again, what's a new, again, another adaptation now is, and as you know, fire has evolved so much in the last couple of years, it's hard to describe it. So what we're doing now is we get loads of questions. So we do loads of what we call interactive wall testing now. So this is where so before we had a wall and floor test, and there are very simple standards that you comply with to do those tests. With these interactive wall and floor tests, there's no standards. So we have to modify the rigs, and we test scenarios that are project-specific scenarios. So in this scenario here, you're seeing an example. It's a world's first. We do loads of these world first tests, and they've never done before because the rigs are designed for different tests. So what we've done here is we pick the wall that we questions asked. We have a 1 hour wall and a half-hour floor. What happens if the half-hour floor fails? Will it breach the integrity of the wall? So we had designed this in advance. We knew we would pass, but again, for the fire consultant, the fire officers, we got this test done and we proved it worked. So, but again, these are what we call interactive fire testing, and they're getting very popular now where we're testing 2 elements. So now we're testing a floor and a wall interacting with each other, okay? So we now move on to kind of module testing, and I think what's most common now in modules or category ones, we generally there's 2 ways. There's a uniformly loaded way of loading the module, or there's a corner post way of more of the module. So what's very important, so when a column is outside the line of a wall, it's a column test. When a column is within the wall, it's a wall test. So it's kind of a rule of thumb. So when we have a column, if it's sticking out of the wall, it's a column. It officially goes into a column test because it has 3-side exposure or 4-side exposure, and that's why we have to do a column test where panels are one-sided exposure. So that's very important. So this is typically a 13381. And what you're showing here is we would do a reference column, which you see a small one, and then we do a full column and we load the column. And like these columns can be loaded to absolutely massive loads, okay, massive loads. And the column, so the important thing to learn here is the column will always expand. And once the column expands, and once the column is returned to its original length, it has failed. That's basically it. So again, we do service penetration testing. I'm not going to worry too much with this, but again, all this testing. So we test everything with the system. It's so important that this is all done. Okay. Now we're going to just touch on BS 8414 testing. And I think there was a lot of this before and very, very topical around Grenfell. Look, it's a very severe test and it was a very good test, but this test really was to test cavity barriers and fire spread within cladding systems. I think that's very important. And there's been a lot of changes in the regulations, particularly in Ireland, UK. And basically this test now, this test was originally designed for over 18 meters. This test is now gone back to under 18 meters. And in the UK now, it looks like it's going to go back to 11 meters. So this test is really, so you'd use it where you have material that's not constructed of limited combustibility. So an A2S1D0. So if all the materials are constructed of A2S1D0, you do not need to do this test. If the materials are construction of that, then you should do this test for a system-specific test. But it's really what they've limited now to 18 meters. So it's really now only being used for legacy issues. And there's another example there. I'll just show you a very quick snippet of one of these. See in a couple of seconds. It gives you an idea of the severity of these tests. And they're a very severe test, and they're again they were a good test. They have a place. So that's just that one. Now we move to full-scale fire testing. So full-scale fire testing is the latest thing. Now the problem with full-scale fire testing is it's incredibly expensive and it's very complex, and you need to know really what you're testing. So there is a previous standard called LPS 1501, and that's kind of a scheme you sign up to. But now we're moving towards a more we're developing this new standards being developed for testing these full-scale tests for Category 1 and Category 2 systems. The idea of the system is it's testing compartment walls, but it's also testing the compartmentation, the fire stopping, the smoke spread between the units. So they're fantastic tests. Unfortunately, they're very expensive. So again, you're testing these kind of details, the fire barriers between floors and concealed spaces, these kind of things here. You're testing all those things. So the purpose of a full-scale fire test is to identify potential modes of failure that cannot be predicted from the results of a standard elemental fire tests to be considered responsive when to realistic fire scenario. Now, as I said earlier on, the elemental tests from our experience, we've done quite a number of full-scale tests. And obviously, we've done hundreds of elemental tests. From our experience, the fire load, the parametric fire loads wouldn't be as severe as the elemental testing. However, obviously, the full scale testing would identify a weakness in the system that wouldn't have been identified by elemental testing. So it could be a junction between a wall and floor, for example, right? So again, these are done by just kind of following assumptions. Like we look at the load density, and what the train of that now is we test the full load. When we say the full load, in other words, we don't allow, even those sprinklers, and again, the state sprinklers are very common, and they're very common here as well. But even allowing for sprinklers, we are now taking no allowance for sprinklers, and we're putting the worst case scenario. And then obviously it's based on the ventilation, and so it's covered by ventilation and fuel load. So just to give you an example of this, we're looking at two technical on this call. So the easier fire is a fast, quick fire. So if you had a window, because you need ignition, you need fuel, and you need oxygen for a fire. So if we take a full scale fire test, so if the window blows out, so if we have the maximum ventilation, if we're like the fire will generally, now what you're seeing here is 2-hour fire curves, okay, typical 2-hour fire curves, and what you're seeing here is it will burn out very quickly because of the, it's a bit like if you a log burner at home and you let the oxygen through, it'll burn out very quickly. And the worst case scenario is if you kind of have half the so a slow burning fire. If you're going less than 50%, there's a good chance the fire won't ignite. So we have to have a right balance. So the worst fire is a slow burning fire, as you can see, and that will last a lot longer, because you see that's the peak of the flash over and it falls off. Okay, so look, this is just a quick snippet of the kind of severity of one of these fires. It's a very quick snippet. Just seeing these are incredibly severe, and the same as the elemental fire test. They're very severe fires, but the issue is they will burn out, because obviously a room can only take so much fuel, so they'll burn out. So to conclude, so loading wall pans, so penetrations in walls are critical. Specialist advice on structural fire testing is required before you start testing. So a lot of people come to us with fire testing, and when we get it, it's no good, because people haven't understood what they're trying to achieve in the fire testing. So really, before you start your test, you need to get real experts on board to guide you what you to test and what information and you need to get to these. Like in all our testing, now we would apply probably 50% more thermocouples than the standards we require, and that's because we're getting loads of very important data. It's important to us. Again, is a product fit for purpose? So remember, with the Offsite system, the purpose class of building is very important. Again, when you're looking at these MMC systems, by all means, speak to your fire officer, your building control, start, make them aware of the technology. And once they're aware of it, they will welcome it, and you talk them through it once you've all the testing. Don't build it and then tell them about it afterwards. That becomes problems. Remember, field of direct application, as we mentioned, is very limited, so don't rely on that. You can get assessments and to 1572. These are special assessments which are extended application. Again, they are more and more limited now than they were. So again, I can kind of state the obvious, a bit more flexible than the field of direct application, but not much. And then obviously the importance of surface penetration is very important with fire stopping, and it's too late construction stage. And then also, from our experience, you need a very good quality management system on site to sign off the fire stopping, and what third-party certifications the system got. So look, I'm just picking an example of Ireland. In England, we have loads of, so in Ireland, we've an SCI argument. So any MMC system in Ireland must have a third-party certification from the likes of NSCI. In the UK, it could be NHPC accepts, it could be SCI, or it could be BBA, for example, or BOPAS. So there's loads of them in the UK, and these are very important certifications. Just to conclude then with once you like, this is an example of one of our clients we work with, and these would be the kind of world leaders in category 1 systems. We do all their R&D, and we've worked with them for a number of years. It's what we call Vision Modular. But you can see on the screen here, they've built all these buildings, and you can see now they're at 44 stories, and they're actually building a 50-story building at the moment in London. Very impressive stuff. You can see the towers. You can see the speed is unbelievable. It's high rise. Look, this is best practice. How it's done, and they have a really good system. Now, obviously, all the systems are lower, but this is a good example of what can be done with MMC, and it's obviously sustainable from the point of view of you can take the buildings down again if you had to after us, but the movements of site, and they're faster, and the embodied carbon is significantly less on these buildings as well. And there's a lot of research being done on that now. Our team are doing a lot of research on that at the moment on this system, but there is very significant savings in embodied carbon on these systems because of the less trades on site, and they have such control of the materials going into the system, so they can really score very well in those sectors. So I'm very conscious of time, and I think I'm just over my time. So I know there's a lot to take in there in that presentation. So I look forward to your questions. Thank you.
Yeah, so thanks so much, Declan. Look, I guess first off, for making the time to present. I know you're, fair to say, you're in demand at the moment and have a busy schedule. So look, I think you've kind of shone a light on the complexity of fire testing, that maybe in some ways there's a reason people stay away from it and defer to experts, but it's really important that people have an understanding, and I think you've done that. A couple of kind of takeaways that I'd have. The first one is that it kind of strikes me that there's a maybe the same way we look at the modern methods construction, that there's a pretty significant chance that we can deliver better quality and the standards for safety for fire as we do with other elements of the construction. Same with the embodied carbon and other things like that. But the kind of question I had for you, Declan, I guess, is your practice is unusual in that, I know you haven't covered this, but you do a lot of other practices within the industry. So we get lots of consultancy requests for our products, and that generally gets us caught on, how does that interact with fire? And for us, we're looking at maybe something like building physics, but you've went ahead and brought in thermal bridging, building physics, embodied carbon, and it's amazing to have them all together, and clearly really important. And while there's a cost, there's probably huge savings in it. But I'm just wondering what made you kind of push ahead with all of those areas.
Yeah, I think it's the solutions. Even the new Part B has been revised, or mainly been revised because of energy. A lot of it has got to do with massive difference in U values and thermal bridging and all. So it's a huge factor to make buildings more energy efficient. That brings challenges in some cases with materials. One of the examples would be, obviously there's a lot of mineral wool being used now instead of, say, rigid foam insulations, right? That's fine, but that brings a whole new area of challenges, because it's a much bigger wall. It's got its own challenges. It doesn't have the same compressive strength. So they bring other structural challenges and I think, so it's all interlinked. And from what we found, we've had to be able to. We've had some very good clients, and they've supported us through the years, and for that reason, that's allowed us to grow our team. And what they really want, especially when you build with MMC at speed, you need answers early on. So the secret to MMC really working at the scale you're seeing there with the likes of Vision Modular is that they have the same design teams on the projects, because they have to make decisions so quickly to fully benefit from the fast track nature of it. For architects and all that, the big challenge is getting all the decisions front-ended. It's such a huge mindset change from traditional practice. So, and that's why we almost have to have this kind of one-stop shop in-house, because, we help with the energy strategy. Energy strategy links to more about overheating, and overheating links down to ventilation, and all this. So it's all interlinked, and, the UV, the glass, the type of that. So it's all interlinked. So we almost have to, we work very closely with the developer and, say, the manufacturer, and making sure both products fit for the challenges and the requirements of that project.
Yeah, no, I can see it, Declan. Yeah, I was in a factory recently, and they had an issue that it happened to be the first one, and definitely for me it was an unusual situation where you could go back 4 or 5 steps and see each module being built, and you can identify quickly the issue. But in your case, if it gets to site, it's happened on so many units. So yeah, there's a huge value to that. And look, I know it from working with other members of your team that there's a huge wealth of knowledge and experience in there. So it's a great asset for the industry. So that's me, I would say. Over to Ben, I think.
Yeah, I think that was a fascinating presentation. I was certainly learning a lot, and it's clear this is a specialist subject. But I suppose one of the things that came out of it for me, I was quite interested in that journey of almost testing material and then testing how that would fix to the next level and getting bigger and then doing the whole structure. What kind of computer modeling of all of this? Is this something that comes in tow with that to predict how fires might spread and what weak points must be? Is that in the testing? I don't know whether that's something that maybe I'm imagining would be a great tool as well.
Not really. Like the likes of test houses and BRE and stuff, we work them a lot. They can predict the fires incredibly accurate. The fuel loads. So once you have the fuel load and ventilation, you'd be surprised. They can really predict the fuel load. They can get the fire really, really accurate, right, to match certain curves. So that's very good, I suppose. Like the reality is, this is there isn't enough data out there. We're kind of unusual that we have done hundreds of tests because we were kind of independent and we work with all these manufacturers. And our goal is really with the manufacturers that's trying to get the pass first time, because fire testing is incredibly expensive, right? And element testing is there. Interactive testing is more expensive, and full scale testing is crazy money. I mean, it's six figure testing. It's very expensive because of the scale of it. Do you follow me? So it's very expensive. So what we're trying to do is make sure, like in this industry. And this is unfortunately, a lot of companies treat it as pure company IP, and yes, I can understand that, but we don't have an open source platform for this, so we have a lot of companies doing the same thing over and over again, and that is a challenge, Stefan, because you can never do enough testing. That's the reality, and even for ourselves now, this thermomechanical modeling is new, and now we're going into even the heat transfer modeling we're doing. Nobody else is doing that because we went to incredible lengths to establish what the materials are doing. So it's not like a normal heat transfer model you get from anybody else. It's a special model based on the properties of on the test of properties of those materials, which is highly unusual. But so it's still at a very early stage, and the reality is that the data is it's so hard to get access to the data. That's the challenge.
So how is this being funded generally?
It's all privately funded. Now there is a in the UK there's a very interesting which we're involved with DLUC, the Department of Levelling Up in the UK. They've started doing full-scale volumetric testing, and now what they're trying to do are full-scale testing on timber, concrete, and steel. And the idea of that is that they will eventually write a standard and that will really set a fair standard. Because at the moment, you could say tomorrow morning you want to do a full-scale test. There is no standard for it as such. The LPS one is kind of a scheme, but it's not a full standard, right? So that we need to develop a standard that is acceptable, that very important, like the fire officers will accept, the fire chiefs in the UK and stuff will accept, and everybody's happy with. And we just need to get to this space because we don't have those kind of standards in place. So at the moment, all the testing is being done individually by companies from their own pockets, really.
Yeah, well, I guess Mike's going to have something to say on that. I'm sure he's thought about fire testing. So I'm intrigued, Mike, what question you're going to ask.
Yeah, so I think, Ben, you touched on one of the questions that was on my mind, which was, Declan, firstly, thank you for your presentation. But the question, two questions rolled into one, really. You touched on the heat transfer modelling that you're at the leading edge of, and I wondered to what extent that streamlines the testing or streamlines the need or potentially reduces the need for some testing. And then I wondered to what extent your existing clients or even you as consultants are looking for standardization of systems to avoid the reinventing of the wheel. And I guess there's some tension between the desire for IP and to have a competitive advantage in a system that is distinct from the next person's, but that's at odds with the expense and the lead time as well for testing, and it's quite a complex area. I just wondered what your thoughts were around those issues.
Yeah, I did the first one, which is the heat transfer modeling. The modeling is key. The modeling is key if you have existing test data to work from. Okay, that's very important. So you need to have, so just say if you're using a Cinia board or a Saint-Gobain board, that you have that board tested, and you have you have all the temperature data and the steel profile. So when you have accurate data, you can use, because without getting too complex in this, I mentioned there Type F boards, and particularly in with the LGS section, with the LGS and all steel category 1, category 2 structures, we tend to use those boards for a reason, because they've vermiculite in them and they're very good at keeping steel cool, right? And it's very important. So, but when you use normal heat transfer modeling, you just use thermal conductivity. So we're able to now, because there's so much data, we're able to get that hard data, and we know very accurately now how those boards protect, and ultimately you'll get much better temperature profiles, and which would be very accurate when you would then if you were to test, if we did a model today and we went to test it to burn it tomorrow, we would expect it would be 20 or 30 degrees of that model, up or down. Do you follow me? They're very accurate. Do you follow me? So now there's a lot of work in doing that now. Trust me, there's a lot of work and expense in doing that, but we've done that, and we think that's going to help a lot, and it would help a lot in predicting fire tests. The second one is an interesting one on the IP. They mentioned earlier on that Evolution were instrumental in setting up MMC Ireland, right? We completely promote people trying to share, and any clients we have, we try to just our clients. Well, you go at the same thing. Will you look at sharing tests? And that's tough, because they might be competing for jobs together. The case is, but look, from our point of view, it's not like the car industry. Our manufacturers in the MC sector are not big. Do you follow me? They don't have 100 million or a billion euro. They have maybe 1 million or 2 million to the business, right? So they can't afford to be spending six-figure sums. Like, for example, I'd always say a floor test is 25,000 euro, a wall test is 17,000 euro. And you won't see 100 grand with 2 or 3 wall tests and a floor test. And that four walls and the floor is 2 floors is 100 grand. These companies can't afford that kind of money realistically. It's a huge outlay for what is almost compliance. You know what I mean? It should be compliant material now. But look, from our point of view, we have to work with what we have, and look, I think it is important that we try and move forward from that, and we try and get more sharing of information. But that is a challenge because of this, just the way the industry is set up globally at the moment.
Well, yeah. I think we ought to hand back to Zach, because time is marching on, and see if we've got some other questions for you that have come in.
Yeah, absolutely. And before we do, I'm just going to do a quick shout out to our supporters. So here we go.
Hi, I'd like to give a big thank you to the fine organizations that make our work at Passive House Accelerator possible. First, a big shout out to our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority. Thank you, too, to our founding sponsors, 475 High Performance Building Supply, Baxt Ingui Architects, Glavel, Minutair All-in-One HVAC and Dehumidification Units, Mitsubishi Electric Train HVAC US, Partel, Rockwell North America, Stocorp, and Zola Windows. And thank you to our champion sponsors, Icon Windows and Doors, Intelligent Membranes, Proseco, and Source 2050. And thank you to our patron sponsors, Aero Aggregates, Brennan, Brooklyn Solar Works, Euroline Windows, Coltraco Ultrasonics Micro Air Leak Detector, Inotech Windows and Doors, Lamelux, Owens Corning, RDH Building Science, Sanderson Sustainable Design, and US Engineered Wood T-Stud. Thank you, sponsors.
All right. So we have questions from Nils. So Nils, are you available to ask your question?
Hey, thanks, Declan, for the presentation. That was really interesting. Great presentation. I'm just calling from Scandinavian Homes in Galway. So I have a question about timber frame testing, if that's something you know about or have been part of before.
Yeah, sure. There's timber frame is quite unusual in Ireland in that they have they have an organisation called the Irish Timber Frame Manufacturers Association, and they've all come together and they've in conjunction with the Department of the Environment, the government, they have tested. So they test together. So they have a fully available list of, which is great to see, of walls and floors tested for timber frame. So it's publicly available. It's free of charge. A supplementary guidance to TGDB. It's called Dwellings 2017, and it's got a list of all the walls and floors that are covered by their testing. So you'll see that they cover walls, floors, and roofs. Roof trusses is the latest thing they've covered.
Yeah, exactly. I've seen the document, but I guess with the cost we were talking about, do you know why timber frame testing is required in Ireland? Because there's pretty normal, like Euro Code 5 structural fire calculations, which are used all across Europe. But then Ireland, England seem to require tests. But for us to develop a new system would be, 4 or 5 tests. That's over €100,000 instead of just calculating. So is there any reason, or is it just become this way?
You need to be very careful calculating. As I said, it's all about the data, and I'd be very concerned about some of the boards on the market. Fire is a life safety issue. We cannot take it. We cannot underestimate fire. Its products. And unfortunately, I'm not a big fan of manufacturers, because a lot of manufacturers and products don't understand don't fully understand their products. So sometimes you need to understand what the product can do. So it's a bit like my very first comment about the non-combustible material. You need to be very sure that product performs very well. So, for example, I'm not a fan of standard plasterboard at all. I think it shouldn't be allowed in fire, because that's my own personal opinion. Because it's got a very high quantity of recycled content, and it's not designed to be a fire protection product. Where a fireboard is a far superior product. Do you find me now? It's different when you're talking 30 minutes, but when you get into 60 and 90-minute buildings, you really need very stable boards that won't crack, that don't crack and fall apart. So, we've looked at it. You really need to know the materials, and even boards from different manufacturers can vary quite differently. So, unfortunately, I'm not a fan of calculation from that way unless you have raw data. But it depends on how different you're going from what's there. But there's definitely, again, you can do lots of kind of assessment, and you plan your roadmap well. You can do maybe 2 tests and get 6 out of it. Do you know what I mean? If you plan it well by just doing it cleverly,
Excellent. Thanks, Nils. So next up is Claudine.
Actually, there's 3 of us here listening. So my name's Cian Davis, and we're just wondering, with regard to testing, you've obviously emphasized the importance of lab testing. And I'm wondering then if you would ever use test by assessment, and what criteria you would use to when you regard that as acceptable.
Yeah, very good question. So basically, I mentioned there's a standard there for test by assessment. So we would generally go back to the lab. So in that situation, they're generally done by the assessments are generally done by UCAS labs. That's the one thing they do. Obviously, they don't consult doing the test, but they will offer you to do an assessment. So anytime they're willing to do an assessment, you can take it that the assessment is. It's very conservative. So if they're willing to offer the assessment and it's positive, then that assessment is fully acceptable, because it is kind of stating the obvious. Now they go into a lot of science there, but it is kind of stating the obvious that they've looked at the temperature. So for example, say there was you want to change, say on a floor, for example, and you had the floor was tested with OSB or something, and then somebody wanted to put a composite deck on the floor. Well, the floor is going to fail. The floor is going to fail based on the board protection anyway. So, for example, the OSB has no real bearing on. So those kind of scenarios, they have no problem doing that. Or what they can do is they can tell, look, the temperature on this board was, let's say, 60 degrees at 1 hour. So if we change this board to another board, then that's fine, because the temperature was so low. That's the kind of stuff. So they are very conservative. So when they are doing it, they're kind of stating, they're taking, look, it's right. They're taking no chances, but. So we use them quite a bit. We work with all the labs to do that. Okay.
Yeah, I suppose to a large extent, I very much agree with you on the idea that test by assessment, if you're going to get it done, have it done by a lab. I suppose, would you ever be looking or regard it as acceptable to use a test that was done for integrity and insulation to then justify a load-bearing test by assessment?
Not really, no. To be honest, sorry. If it had been rigged up properly. In other words, as I said, if all the studs, we'll just say we'll take by the situation. It's a steel wall, for example. If the studs are properly recorded, it's a probably a quarter we could, but generally no. It's very useful. It would be very useful in an overall report. If we had say a loader test, and then we had this maybe as a supporting test, maybe to tell us it would be very useful for a heat transfer model, for example, to give us the data of that board. Like ultimately now, it's very important. Non-load bearing tests and load bearing tests are completely different. So when you say indicative, I presume we generally do indicative tests generally in non-loader rigs, generally, right? Okay, or an indicative test again can be a test that's not fully compliant with the test standard for whatever reason. So it's a bit of a complex question, but it would depend. It's like the answer would be it would depend really on what way we're using it. Okay. Fair
enough. And then one very short follow up on that, if you don't mind, on that one, in terms of then. With either testing or actually with your structural models, then can you take into account the deflection? Because obviously, if you have an unloaded test and then you load it, it doesn't take into account the deflection, and then that would be the same with your FEA models, unless you do some sort of FSI or something like that.
Yes. So what's the question, Keith? Well, what's the question?
So then, I suppose, how would you take into account in your thermal models the effect of the deflecting, which might crack the plasterboard, for example, which you wouldn't?
Well, we would have this. Sorry, the way we did, we would have to have a reference test to start with, right?
Okay, fair enough.
And we would. A very good question now, because again, we want to be very confident that the board will behave quite stable. So, really, what we're after when we do those heat transfer models, really, we're pretty sure the board will stay on. It's just tracking the temperature with different quantities of material. Yeah. Okay.
Fair enough.
Yeah, so we are now at the top of the hour. We do have another question, but I think what we should do first is kind of close out this first hour, and then if Declan still has time, be able to address that question. So Mike, Hugh, and Ben, do you want to share some closing thoughts?
Yeah, again, look, just a huge thanks to Declan. Look, it's clearly a complex specialist area that needs that kind of input, and it's very much not black and white. And look, a long way to go in terms of integration with shared standards for different industries. So yeah, in a way, kind of in its infancy. So, but enlightening presentation, and thanks so much, Declan. Over to you, Ben.
Yeah, I was just going to say something very similar, that it's certainly been one that I've learned quite a lot, and it's going to be a topic that we'll return to, I think, time and again. So thank you, Declan and Mike.
Thanks, Declan. And in the same way that you responded to Hugh's question at the beginning about everything being interlinked, whether it's building physics or embodied carbon or fire, indeed. Passive House. This is the Passive House Accelerator. I think the huge overlap here is quality. Particularly, you've emphasised the need for careful attention to detail with services penetrations, knowing exactly which materials you're dealing with when it comes to the data. There's huge overlap. It's been extremely enriching and interesting presentation. Thank you very much indeed.
Thank you. So, Declan, do you have another few minutes to?
Yeah, sure. Yeah.
Okay, fantastic. Thank you so much. So, Bernard, thank you so much for your patience. If you want to ask your question.
Thank you very much indeed, Zach. And Declan, thank you for an excellent presentation. Just by way of introduction, when I was a young officer in the Irish Guards, aged 20, the firemen went on strike. And so during the winter of 1977-78, we fought fires in central London. And one of the worst fires I ever went to was a wood yard. To give you some idea, this burnt for 5 days. We simply just didn't have the resources to put it out. Anyway, so having fought fires as a young officer, I now find myself back in in fire safety. And there's a huge debate now going on about fire doors and compartmentation. My question to you is, and it's probably a personal opinion, whether you consider that fire doors should close to form an airtight seal, because really the intention of a fire door when closed is to resist the passage of fire and also to act as a barrier for the gaseous products of combustion. Thank you.
Yeah, that's an interesting question. I suppose first and foremost, we focus on structural fire protection. That's our kind of expertise, right? So we focus on making sure that the building doesn't fall down. Basically, it stays standing. Okay, for example, so when firefighters enter it, it's safe to enter and quench the fire, and that's the first priority. I suppose back to your fire doors is an interesting one. I'm not an expert. Fire doors is not an area where we're kind of experts in. It's more the structural fire. But I suppose from a practical point of view, I know myself, when these fire doors become airtight, there is an issue with them closing, because that again, this is a very, I suppose, apt with this air tightness we have now with these modern buildings. They can become very airtight, and the self-closing mechanisms on these doors can struggle to close because of the air tightness. I don't know if you came across that, but that can be a challenge if the building is too airtight. It's a challenge, But I suppose, look, it depends on the fire test, really. Fire doors is very topical at the moment, and I think it depends on. I think we look very carefully at the test on the fire door and how that door has been tested, and with the frame and the seal, and what sort of flexibility is with that frame and seal. But again, most doors are FD30s or FD60s, so we are relying on the sprinklers and the rest and the other systems to get out of the building. I'm not sure if that answers your question, does it, Bernard?
You have. You've highlighted that there is a huge debate because most tragically, most of the deaths at Grenfell were through poison and through the inhalation of toxic products of combustion. And it is a very difficult issue. And you're absolutely right about the closing mechanism and the physical aspects, the mechanical aspects. People have brought forward cold smoke seals, and these seals allow the door to operate with a gap of a few millimeters between the leaf of the door and the floor. And then the smoke seal drops into a groove when the door is actually shut. So this enables the door to shut without any form of excessive resistance due to air pressure. And then once it's shut, it closes to form an airtight seal. And this seems to answer the whole question of acting as a barrier against the toxic products of combustion. Because if you're in a tall building, unfortunately, these gaseous products will reach you and will kill you way before the fire gets anywhere near you. And that's the reality. And that's also why the Building Safety Act, there's a move now towards the frequent and regular inspection of fire doors. And also why this debate is being fought with quite a lot of vigor. But thank you. You're right. Your comments are spot on. There are concerns about the fire doors actually being able to close, because also another thing that fire does, it changes temperature. In changing temperature, you also change air pressure. Thank you.
Thank you, Bernard. Appreciate that. Well, I think that brings us to a close here. So a big thank you to Declan for sharing your insights and this really fantastic presentation. I think you opened a lot of eyes here and among all of us. I know you have for me. Also, thank you to our co-hosts, and thank you everyone for joining us today for the Building Performance Interactive.